In the last modules, we have looked into introduction for algebraic topological methods, and we also introduced some of the basic ideas what relates to the topological dimension and what parameters are connected to what kind of topological aspects. And based on that, we kind of created two types of variables primarily. We looked into source variables and configuration variables. Source variables are the ones which are directly related to electric charges and magnetic poles. In this case, they are going to be D, which is related to Q, and the value of H, which we said we can write it as P divided by S. Of course, you have to exercise certain caution in doing that because this is only magnitude wise equivalent. Obviously, if you take the vector signs and the direction, you have to be sure about the right direction for that. So if you only consider the magnitude, D and H are the source variables. Likewise, the configuration variables are E, which is related to the electric force on a unit charge, and the magnetic force on a unit pole is, again, unit pole doesn't exist, but we are using it only to mathematically say why the E and B are called as configuration variables. So based on that, we were able to create two sets of electromagnetic quantities. They are source and configuration. The combination of source and configuration will give you also energy variables, but we are not interested in talking about it now. It's enough to focus only on source and configuration variables. The next thing what we looked into is, we said there are geometrical objects and they are called as simplexes, and depending on the dimensions of those simplexes, we call them as 0 simplex, 1 simplex, 2 simplex, so on and so forth. And we also looked into a chain of simplexes called as K chain. So if it is a chain of points, it's called a 0 chain. Chain of lines is 1 chain, so on and so forth. So in this module, we will look into further concepts related to algebraic topology. Namely, we will look into the idea of cochains. Here I have used a metaphorical figure containing a bogie with materials inside, like charcoals in each of the bogies. I will explain you why it is metaphorically related to cochains, and then I will discuss the concept of boundary operator, and we will also look into the concept of co-boundary operator and discuss certain properties. So this will be the focus for this module. Okay, let's go into the topic of cochains. Look at this figure here. This figure basically consists of a series of compartments of bogies consisting of materials inside. In other words, what we are seeing here is, we have certain boxes that are tied together. Let's say here there is 200 kilograms of material, here 100 kilograms of material, the same material, and 50 kilograms of the same material. So we can say it's a chain of, like in this case, let's say volumes. So it's a chain of volumes tied together, but whatever is inside the chain, they are called as cochains. So cochains are nothing but the components that we put inside or the components that we associate to certain objects. Let us take a much more easier example. Let us say we have an apartment house, and these houses are 3-dimensional objects, and we can say there are people in the house. Let us say there are 2 people in this house, 1 person in this house, and 3 persons in this house. So what we are telling is it is a volume chain, it is a chain of 3 simplexes, and what we are saying here is the people are associated to this volume. What we can think about it is we can't associate the people to a point, we can't associate the people to a line, so we can't live in the line or we can't live in the point. What we can live is in a 3-dimensional space. So it makes sense to say the cochains are associated to a particular geometrical object. That is what we are going to talk about in the case of electromagnetics. So in this slide what you are seeing here is you have points that are tied together. So it is a chain of 0 simplexes, but each of the point has certain value. It is -5, 1, 3, 4, -2, 6 and so on and so forth. What we are seeing here is nothing but, in the case of electromagnetics, voltages. The voltages or the scalar potentials are the values that we have associated to certain points. So the scalar electric potential is nothing but a 0 cochain associated with 0 simplexes or 0 chains. Similarly, what we see here is we are seeing the potential difference. In other words, the electromotance. The electromotance is always associated to a line, whether it is a straight line or a curved line, it is always associated to a 1-dimensional object. So what we see in this example is the electromotants are nothing but 1 cochains associated with 1 chain or 1 simplex. Similarly, what you see here is fluxes are nothing but 2 cochains associated with certain 2 chains or 2 simplexes. So the most simplest cochain will be values associated to the simplexes. Let me explain this further. We said the chains are so this is the chain. When you use a subscript, we are calling this as chains. So this is a K chain. What we call as cochain, we use the word superscript, C superscript, and these are values assigned to K chains. The question is, let us say I take the simplest chains. The simplest chains are the simplex itself. It has only, so the simplest K chain contains only 1 simplex, let us say K simplex. So it has only 1 simplex. So if I say the values assigned to Ck, when the values assigned to Ck means these are the values assigned to the K simplexes, the simplest K chains. So that is what you see in the slide. So when I say potential associated to this particular chain, what I am talking about the individual points. So we say these are the values written as G1, G2, G3, G4 until Gnk. So G1 could be -5 if it is a 0 cochain. If it is a 1 cochain, G1 can be the electromotance or the potential difference, or in the case here if you are talking about two cochains, G1, G2, G3 can be -2, -8 and so on and so forth. So now we have discussed the concept of cochain. Cochains are nothing but the physically measurable quantities that are assigned to the chains, in other words the simplexes. So let us now discuss the concept of boundary operator. So boundary operator is a very fundamental operator that is going to give us the boundary of a certain object that we are interested in. So what this equation says here is, so this is a k+1 simplex. So what it does is, when I am interested in finding the value of the boundary of certain simplex, what I am interested is I am trying to get the value according to this equation, which says the boundary of k+1 simplex is nothing but certain parameter, what we call it as incidence coefficient, multiplied by the k simplex. So we are going from k+1 to k. So this will become more easy to understand if you understand the physical meaning of a boundary operator. So the boundary operator, which we represent it as the symbol partial derivative, it takes an object, let us say a geometrical object, and it gives the boundary simplexes of that geometrical object. Let us say we call it as M. So let us take a simple example. I give the boundary operator a simplex, a one simplex. Let us say I am interested in an ith one simplex. So what it will give me is, it will give me sigma I equal to 1 to 2, because for a one simplex there are only 2 points. Sum of this a k, I j s I, here I go from 1 to 0. So what I am doing is I am taking an object, I am going from k+1 to k. So if k+1 is equal to 1, what I will get k is k equal to 0. But the important thing is, what is the value of this a, I, j, k for a simplex with points, let us say P0 and P1, and we say the orientation is this direction. The first points a, I, j will be equal to -1, and the second points a, I, j will be equal to +1. So the node from which the line, the arrow points out will be -1, and the node where the line arrow points to will be +1. So this is the way we define +1 and -1 for a S1 of I. So here we are talking about I, which is the element number, and j is the points. So j is 1, j is 2 here. So we can say this is a, I, 1, this is a, I, 2. So the first point ai will be equal to -1 and the second points ai will be +1. So this is what we are seeing in this equation. So j goes from, so this should be j goes from 1 to 2 and aijk is the ith coordinate. So j here is 1 to 2. So let us take the case where we are interested in looking at 2 simplex, a 2 simplex boundary operator. So let us say we have an operator, boundary operator operating on a 2 simplex written as like this, and let us say the 2 simplex has coordinates like this. So P0, P1, P2, and let us assume that the orientations are like this. And we have certain directions that we are choosing. Let us say our surface orientation is in this direction. So this is S2 of I. So let me write it down again. So this is S2 of I. So in this case what I am looking at is, I am looking at likewise is equal to sigma j goes from, so here the j will be the boundary elements which are nothing but the lines themselves. J goes from 1 to 3. So I will have a I j s k plus 1 is equal to 2. So we have k which is equal to 1. So now we are interested in knowing what are the incidence coefficient for individual 1 simplexes. So let us take this example, say we are going from j equal to, so this is j equal to 1, this side equal to j equal to 2, this side is j equal to 3. So what we are getting here is the first component will be minus of the direction in which my orientation is there. So my orientation is in the anti-clockwise, but this is pointed in this other direction. So this will be minus 1 s of, so this is, sorry, j. So the first component will be equal to S1 1 plus the second component will be, is the second component is in this direction. So it is also in the opposite direction to the orientation. So this will also be equal to minus 1 S1 2 and plus the third component is in the same direction. So we will have plus 1 S1 3. So for this example what we have is, we have minus S, so the boundary operator operating on S I of 2 is equal to the value that we have got here, minus S11 minus S12 plus S13. So this is what we are seeing in this slide. Remember our old example where we had a set of values given by the problem what we had. So I am going to show you the problem one more time. So this is the problem we are talking about. So we had certain values of directions we have chosen already, and we have also computed the value of various triangles. So let us quickly see what will be the value of the boundary operator for one or two cases, and we can, based on that, we will deduce the other values. So let us take the first example where we are interested in finding out the incidence coefficient for a particular set of values. So for that I will keep this bigger triangle. So using this we will see that we have to compute the value of various boundary operators. So the first boundary operator that we are interested in is the value that is given by A1. So A1 is the boundary operator operating on one simplexes. So 1 operates on 1. So what we are getting is A1 will be a matrix that has number of edges times number of nodes. So in this example what we see is we will get certain A1 matrix. So I am going to compute the A1 matrix for this example right now so that you can get a physical sense of how we are computing it. I said A1 will be having number of edges. In this case, as you can count, there are totally 7 edges. So the edge number 1, edge number 2, edge number 3, edge number 4, edge number 5, edge number 6 and edge number 7. So what we are seeing now is we will write down all the edges. So these are S1, S11, S12, S13, S14, S15, S16, S17. So these are the 7 edges, and we said the rows will be the number of edges and the columns will be the number of nodes. So we have totally 5 nodes. These are given by P0, P1, P2, P3 and P4. So let us write them down. So we have P1, P0, P1, P2, P3 and P4. So now we are going to populate this matrix purely using the information that we have got in this slide. So let us do that one by one. So what we have got here is, let us look at the slide. So what we have is, for this node there are only P0 and P1 that are connected, on all other things are 0. So we can safely put 0, 0, 0 for all other things. For P0 and P1 we need to know whether it is +1 or -1. So if it is going away, I said it is -1, if it is going into, I said it is +1. In the same way, let us look at the case of P2. For P2 the nodes that are associated are P1 and P2. So I can put 0 for all other things. So I am putting 0 here for all other things except for P1 and P2. But I see the node which is going away is P1, so it is -1, and the node where it is going into is +1. Similarly for P3, what we see in this graph, it is P2 and P3. For all other things I can put 0. I will put 0 for P0, P1 and P4. For P2 and P3 it is going away from P2, so it is -1, it is going into P3, so it is +1. Similarly for P4, for the fourth line, what we see is only points are P0 and P3. The rest of the things I can put 0, 0, 0, 0. It is going away from P0, so it is -1. It is going into P3, so it is +1. For S15, likewise in the graph, what you see, the value for S5, it's P1 and P3. So the rest of the things I can put 0. So it's going away from P1, so it's -1. It's going into P3, so it's +1. For S16, it's P2 and P4, they are connected. So the value is 0 for other nodes. So P0 is 0, P1 is 0, P2 is not 0, P4 is not 0, but other things are 0. So I am putting zeros for other things except for P2 and P4. So it's going away from P2, so it is -1. It is going into P4, so it's +1. Similarly for S17, the last one, P3, it's going away from P3, so it is -1, and it's going into P4, it's +1. The rest are 0. That's what I am putting in the graph here. So you can see here in the slide, the final matrix what we will have is as follows. So as you can see in the slide here, so this will be the final matrix of A12, and that one is what we have represented here in the next slide as a transposed matrix. So we have taken A1 and we have taken the transpose of this. Similarly, we can do the same thing for the A2 transpose, where we will have A2 will be the number of surfaces to the number of edges, and the transpose of this is given here. So let's do the case of A2 matrix for us to get certain confident on what it is, and then we will take it from there on. So let's look at the slide here one more time. So we are interested in A2 matrix whose rows are given by the number of surfaces. So we will have 3 surfaces. They are written as S2 1, S2 2 and S2 3, and we will have the column as number of edges. So what we have here is S11, S12, S13, S14, S15, S16 and S17. So we have 7 columns, and we have 3 rows. So when we look at the first graph, what we see here is, so the first, for the S12, the first one is in the same direction, the second one, the S1, so there are 3 edges, so we have 1, we have 5 and 4. So 1, 5, 4 are non-zero and the rest are 0. So we can already do that in our graph. So except for 1, 5 and 4, I put 0 for others. And for 1, it is in the same direction, so it's +1. For 4, it is in the opposite direction, so it's -1, and for 5, it's in the same direction, so it's +1. So what you see here is basically from the graph here. 1 is in the same direction, 5 is also in the same direction, 4 is in the opposite direction. Similarly for S22, it's the subscripts 2, 3 and 5 are non-zero, 2, 3, 5. Except for that, I put 0 on other things. 2, 3, 5 are non-zero and the rest are 0. So 2 is in the same direction as that of the curve, so you can see that here in the graph. So 2 is +1. 3 is also in the same direction as you can see from the graph, so I put +1, and 5 is in the opposite direction, so I put -1. Similarly for the last triangle, 3, 7 and 6 are responsible. What we have is 3, 6 and 7. Except for that, I put 0 on other things. 3, 6 and 7 are non-zero. So 3, 6, 7 are non-zero. So 1 is 0, 2 is 0, 4 is 0. So 3 and also 5 is 0. So 3, 6 and 7 are non-zero. So let us look at what is 3. 3 is in the same direction. So we put plus 1. 6 is in the opposite direction as you can see in the graph. So we put minus 1, and 7 is in the same direction, so we have plus 1. So if we take this one and we do the transpose of that, what we will get here as the A2 matrix. So what we have done now is we have looked into the boundary operator, how we are defining the boundary operator. We have taken this from a simple example. In the next module we will look into the topic of co-boundary operator, which is the counterpart of the boundary operator, and also we will discuss certain properties. So with this we will end this module. See you again in the next module. Thank you.